Hi all, my name is Lamar Watson. Today I'm going to be presenting my topic on machine learning. Uh, Basically, I'm very new to this segment of computer science, so before I started this class, pretty much my idea of what AI is in reference to the 1984 movie The Terminator, where intelligent machines are pretty much going to take over the world and kill all us humans. So I thought this was a good introductory to what exactly is machine learning and how closely aligned is it to what Hollywood would have us believe. So let's go ahead and get started. I wanted to start with the overall question that I first asked, which is what is learning and how do we break that down into a systematic approach which computers or machines could mimic. So I came up with the very simple scenario where someone touches a hot stove. Painful, ouch, it hurts. You don't want to touch a hot stove. So we would classify this as a negative experience. It wasn't fun, it was bad. We shouldn't do it again. So we create a rule. Don't touch hot stoves. This is how we learn. So that's all well and good, but I have another question for you, and that is why do we associate the color red as hot and the color blue as cold? So when you think about it, the color red signifies fire and hot things, and the color blue tends to signify ice and not hot things, so cold things, water. So, to me, learning is essentially a classification process. We classify outcomes based on what we've experienced in the past. So, machine learning is also a classification process, but it's one which utilizes raw data. So, obviously, a computer can't touch a hot stove, but given the data, it could assess temperature ranges and create a classification process. So that leads us into what exactly is machine learning. So machine learning is a sub-branch of artificial intelligence. Sapphire, a professor, he explains it as learning to do better in the future based on what was experienced in the past. So he does a lot of theoretical machine learning at Princeton. I actually reviewed some of his slides, very detail oriented. So really our main goal is to learn from the data without the need for programmed algorithms to determine every possible outcome. So someone like me who comes from a programming background, it's kind of a different concept in terms of having this loosely coupled outcome based on something that you're not directly programming. So you take a computer-based classification process. It utilizes data and it's going to pretty much spit out a classification at the end. So there's no linear procedural code to step through. It's going to come to its own conclusions using data and grouping processes. So within machine learning there's two main categories. The first is supervised learning. My example I like is this little kid where his dad's helping him learn to walk, so he's being supervised. Supervised is defined as to watch or direct someone or something. So when we create a supervised learning, we're really providing a sample set of data to train or learn for our machine learning algorithm. So if we go back to the example of temperature, we would be providing a data set similar to this, where we have 0 means cold, 32 means cold, 100 means hot, and 150 means hot. So we can provide this data set to our machine, and it's going to learn from this set, and it's going to be able to classify outcomes, future outcomes, based on unseen temperature values. So for example, we could then provide a temperature data set like this one where we say, okay, what is the outcome of 15 degrees Celsius and what is the outcome of 175 degrees Celsius? So the little computer says, well, I'm smart enough to know 175 is hot, but I can't be burned. The next large category is unsupervised learning. So this to me is kind of where no parental guidance can also lead to valuable learning experiences. So much like the pictures demonstrating, look ma, no hands, we're going to see how to classify this experience. So back to machine learning, in this circumstance we would provide no labeled or training set to learn from. So we simply just are going to give the raw data to the machine learning algorithm and let it decide how to classify it and group it. So the question becomes, how do we do that without giving it the learning or training set example? So the machine is going to have to use a different strategy to decide how to classify these outcomes. So essentially what it's going to do is it's going to create clusters or groupings of the data. So here we can walk through the example. 0, okay, that's the lowest value. 175, that's the highest value. 32, well, that's more like 0 than it is 175. So it groups it closer to 0. 100 is more like 175, so it groups it like 175. So it'll go through and figure out, how to create logical groups based on quantifiable values. So here our bot is saying, I have created you groups, but I'm not sure why. So within supervised learning, we have different methods: neural networks, decision learning trees, naive Bayes, random forest, case reasoning, linear regression. Within unsupervised methods, we have clustering and hidden Markov modeling. What you'll notice is there's a lot more methods for supervised learning than there are for unsupervised methods. And this is simply because unsupervised methods is really just different ways of creating clustering, whereas supervised methods provide much more granularity on how to control the learning outcomes. But the real question we have is, which one is going to give rise to the machines? My personal theory is that this will be the support vector machines. So this is what I've chosen to focus on for my AI project. It falls under the category of supervised learning, and I'll explain a little bit more in depth how SVMs, as they're referred to shorthandedly, work. So SVMs are a supervised learner with a sinister name, but they're not that dangerous yet. So this is a training set from a genetic-based experiment that I'll be discussing a little bit further. Essentially what we need to know right now is we have different classes of data. So we have a purple cluster up here, which have been labeled class 1, and we have this green cluster down here, which have been labeled class 2. So these two classes are the known data set that we're going to give to the SVM to train on. All the red dots are unseen data samples within the same data set, but we're not going to provide any outcomes yet. So here we can clearly see there's two different distinct groupings of data, class 1 and class 2. So what the support vector does is it attempts to draw lines, support boundary lines, between the two groups to find where the division is so that it can classify the future dots. So essentially the algorithm, it's a mathematical model. It figures out every vector between the two categories or groups. So here you can see all these crazy lines, and you could take any one of those lines and say that that's the boundary between the two groups. But how do you know which one is the ideal boundary? And this is really where the support vector comes in. It forms the mathematically most correct, maximizing the distance between the two groups of clusters. So here we can see that this is the true boundary between the two classes of data. So going forward, we can predict which class the unseen data sets will most likely belong to using the ultimate support vector. So I wanted to talk a little bit about current trends. I wanted to do something a little different. I wanted to actually go out to the marketplace and see what's actually going on with machine learning. So I went out to a popular job search site, Indeed, frequently used by myself, typed in machine learning, and I wanted to see what came up. So the first thing I wanted to point out is the number of jobs. There's 3,944 jobs. And this is across the US. There's no state filter on it at all. Quite a few number of jobs, but when you compare it to software engineering, there were 112,000 jobs for software engineering. So machine learning is representing about 3.5% of all software engineering jobs. So it's a very niche area to be working in. But that can also be a good thing, because if you specialize in it, you might not have a problem finding a job. So Indeed also has a trending area that you can use to type in anything you want, whether it be skill sets, jobs, things like that, and it tracks the trending. So here we're looking at a graph of the number of postings with machine learning, and you can see this nice trend from about 2008 onward, just a steady increasing line. So the question is, what caused this huge spike? That I honestly don't know. I do have one theory. I'm not sure if it holds any water though, but I'm not sure what caused the spike. So I decided to continue to delve in and look at some of these companies who are looking for this particular skill set. So I wanted to kind of highlight them very quickly. There's a company called Data Pop Marketing. Essentially what they do is design analytics and machine learning that makes intelligent ads. So their premise is that instead of using Google and just getting blasted with shotgun approach ads, they can help really design algorithms to solicit exactly what you're looking for. Ancestry.com, they're using data mining and machine learning to support user profiles and behavioral analysis. They are very data heavy, data centric, so they're doing a lot of interesting things with data mining and machine learning. SRI International is using it. They're looking for someone who can do text classification, document clustering, and machine learning algorithms for US government and commercial clients. Retail Me Not is looking for new ways to learn from real data so they can help millions of customers find the lowest prices on the products they love. And of course, a heavy hitter, IBM, is developing brain-inspired technologies to transform the way we interact with each other and the world. They're trying to partner cognitive system science with machine learning to create interesting insights. So, now that we've kind of highlighted some of those current trends for machine learning, I wanted to give a couple of real-world examples of how machine learning, and in particular support vector machines, is kind of changing the science of how we're doing research. So there was one study I read that was pretty interesting, where they're basically taking corporate and municipal credit ratings, and they're learning how to predict what those ratings should be. So kind of these ratings are very similar to what a person would have for like a FICO score, only they're for very large investment grade entities. So like governments, countries have ratings. So you might hear the U.S. is a AAA rating. This is what it means. It's investment grade, the highest quality credit risk, very low risk. And it goes all the way down to D rating, non-investment, in default, highly speculative stuff. So what they're doing is they're taking the probability of repayment of principal and interest. They're feeding in 52 different parameters from their database and the S&P database, and they're trying to predict, using those 52 parameters, the outcome, so the classification of what these entities will receive for a credit rating. So they're using all these different AI and machine learning methods, which you can see in the method column. And essentially they're correctly predicting, on the very far right column, the test percentage. You can see the accuracy of their predictions. So some of these are approaching very high figures. 80% accuracy is very high. So they're correctly classifying 80% of the credit rating based on these 52 parameters. So that's pretty good for, just classification and using support vectors and machine learning methods. Another real-world example is in genetics. There was a study done where they were attempting to further improve genetic algorithm training, which is for gene selection, identifying genetic crossover, being able to predict genetic mutations, things of that nature. So what they did was they took improved gene classification by implementing different variations of support vectors. So typically support vectors are using one type of learning, typically supervised learning, where you're providing it a limited subset of data to train on, and then you're using the unseen data to actually form predictions. So what they decided to do is kind of form their own hybrid between supervised and semi-supervised training data sets for their SVM. So on the left we're looking at what their unique algorithm is doing, and then on the very right, the SVM Lite, that's your traditional supervised learning SVM. So here on the right we can see they're approaching 6%, 7, there's a 13. And then with their hybrid solution using the SVM, they're getting slightly better numbers, but much more consistent numbers. So 6s and 7s and 8%. So what I would like to talk about now is what I've been working on for my AI project. I'd like to call it the Securities Trading Predictor. It's STP for short. It's essentially an intelligent solution for determining buy-sell indicators for financial stocks. So it's using supervised learning, and it's primarily using support vector machines to classify data sets. Real quickly, I just wanted to go over the system architecture. Essentially, I am grabbing data sets from various sources like just downloads, historical data downloads. I'm then saving them as CSV files and then doing some manipulation with formulas just to kind of generate some different elements to evaluate. I then take these spreadsheets and I load them into a MySQL database. All the implemented code is using Python to do this. Once it's in the STP database on MySQL, I can then start performing and using my training sets. So I create a training set for the data, and then I feed it to the SVM. The SVM learns from that training set, and then I can take a flat file prediction set which hasn't been seen by the application yet, and it's going to attempt to classify that data set into a buy or sell category. So I do want to now show you what this looks like. Please ignore my cluttered background. This is the main GUI that I've created for the STP predictor. I try to keep it as simple as possible so that I could focus on implementing the machine learning algorithms. So essentially my dropdown is just 10 stocks that I've selected. I downloaded 2 years of historical trading data for every day for each of these 10 stocks. And this is what's going to serve as my training set. So I have this functionality to import the CSV file and then view the security. So what's going to happen is I've created a test file. So this test file I'm going to then run. I took this, which hasn't been used by the learner, so that I actually know what the outcome really was, and I'm going to run my predictions on this test file. So what happens is I generate a prediction. This takes about 60 seconds to run because I'm using the full 2 years of daily trading data to train my SVM on. So once it's done forming the SVM, it's going to now open up the test file and try to classify the outcomes. It is now ran through that file, it's formed predictions, and it's reloaded it to another table in the database. And now I can view the predictions that it's made. So here I have my different stock tickers, the date it was created, and here's my prediction for what to do with that stock based on the temporary data set. So I'm still definitely working on tweaking my system and getting it more accurate. It's incredibly challenging trying to figure out exactly how to maximize the accuracy of the predictions. So this concludes our presentation for today. I hope I've explained kind of the overall process of what machine learning is, the two main groups, supervised, unsupervised learning, particular how support vector machines work and classify, and I look forward to viewing everyone's presentations, and I will be posting this topic, and if anyone has questions I will try my best to answer them. Thank you.